Hi everyone, in this video we're going to solve the electricity for physics unit 2, obviously A levels AX, and in this entire worksheet we're just going to only focus on electricity. That means in this entire worksheet we're going to cover current, charge, potential difference, resistors connected in series, in parallel, and internal resistance, EMF. All these concepts will be covered in this entire worksheet. Now again, all these questions that are compiled in these questions are actually taken from your question papers, like your actual question papers provided by your Edexcel Pearson, and I have arranged them into different topics. So only for this video we're going to focus on the MCQs, and again there will be a second part where we are going to focus on that theoretical questions. And for the theoretical questions, we'll explain that how to connect every questions with each topic, and how to also write that asterisk mark questions for that 6 markers. Okay, enough of talking. Let's start with this video. Okay, now over here we're going to start with current and charge. For current and charge, the one equation that should obviously pop up in your mind at the very start is Q is equals to IT. Charge is equals to current into time, right? So I'm just going to write it at the very top. Q equals to IT. Now, this equation is very frequently used in terms of current and charge, and also there are other equations for electricity, which we'll obviously see along as we solve other questions for this. Okay, so we're going to start with question 1. It says that which of the following graphs for potential difference against current correctly shows the behavior of a filament lamp? Now, clearly see that this is talking about voltage against current, right? In your book also maybe, and also in our classes, if you're going to join our classes, you can also see that in our classes, I always explain there are two types of graphs for IV, for that filament, and again for that negative temperature coefficient conductors, which are like thermistors. Okay, these are the two axes. I will reverse the quantities on each axis. For example, in the first one, I will write I on the y-axis and V on the x-axis. Now, what exactly happens in a filament lamp? In a filament lamp, initially the current flow is extremely high because resistance is very low. But finally, what happens, like over a long period of time, when the filament lamp is switched on for a long period of time, due to current flow through that filament lamp for a long period of time, temperature will increase, and that will cause the resistance to increase, right? Filament lamp are actually positive temperature coefficient conductors. So as we're going to turn on the filament lamp for a longer time, current flow will obviously be there for a longer time, which means that because of that current flow for a longer time, there will be a temperature increase, and because of the temperature increase, the resistance of the circuit would increase. So in that case, initially the current increase will be very high, whereas finally the current increase will be extremely low because of the high resistance. So in filament lamp, initially I is very large, and finally I is very small because of the change in resistance that occurs for this entire transition. So in this case, the graph is like this. Initially the I is very large. That means initial section of the graph will be more steeper, and final section of the graph is supposed to be less steeper. So this is how the graph would look like. Right, but the problem is that this question they're not asking you about current against voltage. They are specifically asking you about voltage against current. So they have reversed the voltages, reversed the quantities on your graph. So in that case, now you have voltage on the y-axis and current on the x-axis. So the shape of the graph will also be different. Now you have this kind of shape. 1 minute. This kind of shape, which again indicates what, that you can clearly see that initial part you get for a very small increase in voltage, you're going to get a very large increase in current, and for the final part you're going to get a very small increase in current for a large increase in voltage, right? So that concept is still the same, right? That for initial section current increase is very high, for final section current increase is very small. So in that case, only this portion was represented on these 4 options. We can clearly see C is the correct answer over here, right? So final answer over here is C. I hope this was clear for all of you to understand. If there's any more questions, you can certainly ask me in the comment section. Okay, let me just write one thing over here in extra, that what was I speaking? Wait 1 minute. Yeah, I was thinking that initially current flow large. Okay. Initially current flow large, this causes temperature to increase, so temperature increase, and because of this temperature increase, resistance of the circuit, this also increases, and again because of this resistance circuit, final case the current flow will decrease. So finally current flow decrease. So this is like a flow chart that you can remember for these kind of concepts. Okay, now we're done with question one. Moving to question two, a rechargeable cell carries the marking 150 milliamps hour. What charge does this correspond to? There was a typing mistake, sorry, the 2 was not supposed to be here. So 150 milliamps hour, what does this indicate about? Milliamps gives you the amount of current, and hour means 1 hour, right, which obviously has to be converted into seconds, because according to your equation q is equals to it, time is always measured in seconds. So now you have to measure the value for charge. So you can write q equals to it, which is 150 multiplied with 10 to the power of negative 3 multiplied with 1 multiplied with 3600. Right, over here 10 to the power of 3 converts that milliamps to amp, and 3600 converts that 1 hour to seconds. So now if you calculate this, you're going to get 540 coulomb, which is obviously option B over here. And that was everything that needed for this part 2, right? Other than that, nothing is that much needed over here. Okay, so I hope that this question 1 and 2 was clear enough for all of you. We're going to move on to the next question. In question 2, it says that an electric motor with potential difference V and current I lifts a mass M through a height h in time t seconds at a steady velocity, at a steady speed V. The efficiency of the motor is given by. Okay, let's just see a visual representation for this entire scenario. Um, Okay, so there was a motor who is actually lifting something from ground, right? That means if you're lifting something from ground, it is increasing its velocity. Its velocity is increasing with time. Sorry, its height is increasing with time, because maybe it was at a ground level, or even if it was not at a ground level, it was a certain meters above the ground level. If you're going to pull it or lift it right above that point, its height is still going to increase, right? So in that basis, over here the total output energy that was actually provided for this useful case was gravitational potential energy, and input energy will be power, because you're working with motor, you have a voltage, current and time, right? So obviously we're going to connect it as power. Power is your total output, total input, and gravitational potential energy is your total um, output. Okay, so we're going to write it down this as energy is equals to power into time, which is power can be broken down into VIT. Right, this was your total energy input, or total power output, not power, total energy input. And total energy output was, let me just write this down. This is total energy input, and GPE, gravitational potential energy, was your total energy output, which was MGH, right? So this is your output energy. Okay, now if you want to find out the efficiency formula was useful energy output divided by total energy input. In that case, we can write useful energy output was mgh, and total energy input was that vit, which you can clearly see is very similar to option D, right? It has this gravitational potential energy in the numerator, and power into time, which was equals to energy in the denominator. So obviously option D is the correct answer for this question 3. Yeah, that's it. If there is any question, you guys can obviously ask. Other than that, there was nothing much for this question. We're going to move on to the next question. This one says that the graph shows the variations of potential difference V with current I for three components. The three components are a metal wire at constant temperature. That means it's talking about ohmic conductor, right? Where obviously at constant temperature, current and voltage remains proportional. And we can clearly see this one is that one, right? Only in the graph for particle N, the graph was a straight slant line between the voltage and current, right? So only this one shows for that ohmic conductor where current and voltage are directly proportional. So we can write this is directly proportional. So obviously this is the graph for the metal wire at constant temperature. And again for the filament lamp, we have already seen at the question one that this is your filament lamp graph, right? Like same situation over here. Initially the current will be very high, finally the current will be very low because of the increase in resistance, because of the increase in temperature. So this is for your filament lamp. Filament lamp. And again, M is for diode. Only difference over here is that always in our exam papers, not exam papers, always in our books we saw graphs as voltage on the x-axis and current on the y-axis, right? In these questions they have reversed the units. So in most of the cases, the voltage graph, current voltage graph for diode that you saw was this, right? Almost zero, like the current flow for these diodes will be almost zero until you reach 0.7 volt, and after this the diode, like the current flow in the diode increases very steeply, right? Now in this same situation, if you're going to reverse the voltages, reverse the axis, in this was a diagram for current against voltage. If they want to draw a graph for voltage against current, then it will be different like this. Up to 0.7 volt, current will be extremely zero, and after 0.7 volt the current will increase all of a sudden, right? So if you match, this is exactly option M, right? So option M was, or the graph M was represented for your diode. In that case, this is for diode. So we just have to match this with the following answers. M is diode, so diode M, and L is filament lamp. Right, so M is diode, L is filament lamp, and N is your ohmic conductor. So in that case, option D is the correct answer. So this is how you're going to connect all the points with your graphs and find the final correct answer. I hope this was clear enough for all of you to understand. We're going to move on to the next question. This one says that a student wants to find the internal resistance of a cell. He plots a graph of the potential difference across the terminals of the cell against the current through the cell. Okay, which of the following gives a internal resistance of the circuit? Now over here, potential difference, current, right? This potential difference is actually the potential difference across that fixed resistor which was connected in series with that internal resistance. Now in this situation, the formula was always represented like this. VR, potential difference of that fixed resistor which was connected in series with the internal resistor, is equals to minus RI plus EMF. This was exactly in the form of y is equals to mx plus c, where obviously this y coordinate, which is approximately 2.5, 2.6, right? This is the value for your EMF, the total voltage supplied by the power supply, and mx was your current, right? So x, on the x-axis we have seen current, on the y-axis you have voltage. In that case, the gradient will give you R, but it's not only gradient, it gives you negative R, right? So in that case, as we are working with resistance, right? Resistance are actually scalar quantities. So only the magnitude part will be focused on. The negative sign in front of that R doesn't actually involve anything in this case. It is only negative because that graph was a downsloping line, right? Because of that downsloping line, you got the internal resistance as negative. So in that case, the magnitude of the gradient will give you the value for the internal resistance. They have specifically stated the magnitude because we are not focused on the negative sign, as internal resistance is a scalar quantity. So to be very specific, the magnitude of the gradient of this voltage and current graph will give you the internal resistance of this power supply. Okay, the area under the graph doesn't give you anything. The intercept on the current axis also doesn't give you anything. The intercept on the potential axis gives you that EMF. We have already stated that, right? For A and B, we do not get anything from that part. No, for A and B, we can also find out the power of that entire circuit, right? Because for area under the graph, you always multiply the y-axis with x-axis, which means that you're going to multiply voltage and current together. For voltage current, you get power. So part A, you get power. So IV. And the intercept on the x-axis, the intercept on the x-axis indicates when voltage was zero, this was the current flow, which is completely not correct. So part B doesn't give you anything over here. Okay. So yeah, this is it for question 5. I hope it was clear enough for all of you to understand. We're going to move on to the next question. Electrical power is transferred to a motor as shown. This is the total power input. This is the mechanical power output. So obviously this is the useful one. And power loss. Obviously this is the waste. If you want to find out the efficiency, the formula for efficiency was useful divided by input. Now in this case, useful was P naught and input was PI, right? So in that case, also not P naught, that's PO. P output divided by P input, which is option D again. P output divided by P input. So question 6 also has the answer is option D. Moving to question 7, the amount of electrical energy transferred to a charge of 8 coulomb through a potential difference of 12 volt. We want to connect our equation with charge, energy and voltage. That is E is equals to VQ. And electrical energy is equals to voltage into charge. Now the charge was in milliamps, so obviously we have to convert that into like millicoulomb. Obviously we have to convert that to coulomb, so which is going to be 8 multiplied with 10 to the power of negative 3, and that also multiplied to 12, right? I think for this, let me just calculate it. The option answer is C, because you get 0.096, right? So over here you get 0.096, which can be written in standard form as 9.6 into 10 to the power of negative 2, which is obviously option C over here. Okay, now we're going to move to question 8. It says that a resistor connected to cell, a resistor is connected to a cell. The amount of charge passes through the resistor with time t. During the time, the amount of chemical energy converted to electrical energy by the cell is E. Which row of the table? Which row of the table correctly gives the current in the resistor and the EMF of the cell? Okay, let's just draw a circuit over here. There's a cell over here. Okay, the circuit was connected to a cell. Okay, so one cell. A resistor connected to a cell, amount of charge Q passes through the resistor in a time t seconds. During this time, the amount of chemical energy converted to the electrical energy is given by E. Like over here, the total like power supply for this cell was E, capital E, and they want you to find out the current through the resistor and the EMF. Okay. Hmm. The chemical energy to electrical energy. Oh no, this was not the EMF. They have given you the value for the total electrical energy, and they want you to find out the value for that total voltage. Well, EMF is voltage, right? So you can write EMF is voltage. And they've also stated that what was the amount of total charges passing through the resistor? It was Q. So if you want to find out the voltage, you have to just rearrange the equation. So E is equals to VQ. I'm just going to write V the subject, which is going to be E over Q. That means my correct answer is either from option A or option C. And after that, they also want to find out the value for current. They have given you charge and they have given you time t. In that case, Q is equals to IT will become I is equals to Q over T, which is again option yeah, option C is the correct answer, right? Sorry, I made a mistake. This was not division over here. So my correct answer over here is C. Okay. We're just using these concepts only. Like the only confusion for this question was that they were not giving you anything about the data. It was all about in terms of alphabets. For example, charge flowing through that resistor was q. Time taken for the charge to flow through the resistor was t seconds. Using that q and t, you can measure the value for current flowing through that resistor, and again the value for the electrical energy, which is basically the total energy divided by the charge passing through the resistor, can also be used to find out the EMF, because it doesn't have any internal resistance this time, right? So calculations for your series circuits, parallel circuits will not come into any consideration. So yeah, that is just it. We're just going to like simply reverse the formula, simply like rearrange the formulas. Other than that, nothing else is required in this part. Okay. Which of the following current potential graph correctly shows the behavior of a diode? We can clearly see option C, right? Let me just understand or explain every one over here. Now remember, focus on the axis in this type of graphs. They always try to make it more confusing by reversing the axis every time. For example, in all the previous graphs we have seen so far, voltage was on the y-axis and time was on, so current was on the x-axis. This time they have reversed the axis again. Now current is on the y-axis and voltage is on the x-axis. Now in this case, the first one is for ohmic conductor, where obviously voltage and current are directly proportional. So this is for an ohmic conductor. Metal wire at constant temperature basically. This one, initially it's steeper, finally it's less steeper. That means this is for a filament bulb or positive temperature coefficient conductors. So we can write filament or positive temperature coefficient conductor. And part D, initially it has less current, finally it has more current. This is for thermistors. Thermistors. Like similar kind of graph can also be created for LED, but if we're talking about light intensity, then only, because obviously LED is also behaves like a negative temperature coefficient conductors, but only difference is that negative temperature coefficient conductors depends on temperature, obviously their name suggests it, but LDR is dependent on light intensity of the surrounding. Otherwise, same property, same kind of working. So thermistors, these are for negative temperature coefficient. Sorry, I'm obviously not writing the full forms. I hope by this time, since you guys are going to sit for the exams within a month, you guys know the full form of coefficient, spelling of coefficient. Okay, so now in that case, obviously option C represents the graph for a diode when current is passing through it, which obviously over here up to 0.7 volt, the current flow will be extremely low, because up to 0.7 volt, the resistance is extremely high. After passing or after overcoming this 0.7 volt, the resistance drops down and current can easily flow throughout the circuit, throughout this diode. Okay. Okay, so this was it for the current charge MCQs. Now, if you have any problem from all these current charge MCQs, please don't hesitate to confront me or communicate with me. So yeah, thank you. We're going to move on to the next part, which is resistors. I saw, right? Yeah, this is for resistance, and also this is also a part for the combinations of questions from series circuits and parallel circuits. Before we start, there are a few things that we need to remember. That is, in series circuits, current stays the same, voltage is divided, and because of the fact that voltage gets divided as you're going to add more components in series circuits, so the dullness, like the brightness of each component, is going to decrease every time you're going to add a component to that circuit. Because for example, if I start a circuit with two resistors, right, in that case they were going to receive equal amount of voltages, maybe because they have the same amount of resistance. But if I'm going to add another component into that scenario, now that entire voltage is divided by 3, right? So now in this situation, when we are going to add more components to a series circuit, the voltage will drop down for individual components. So now individual components will receive a smaller voltage, and for a smaller voltage they will certainly glow at a like lower brightness, lower light intensity. And again, for parallel circuits, voltage remains same, so their brightness or dullness are not modified. Doesn't matter how many components or how many appliances are you going to connect in that parallel circuits, but their current gets divided in parallel circuits. So you're going to write this. I same, voltage different, and for parallel circuits you have voltage same but current is divided or different. Again, because of the voltage gets divided among each component, this causes dullness. Okay. Another thing, the equation for the resistance for these two different combinations of circuits are different. For example, in series circuits, the total resistance of the circuit is basically simply the total number of resistors, like the summation of the total number of resistors connected in that circuit. For example, in a circuit, you have two resistors connected in series. In that case, the total resistance would just be the normal summation of the two resistors, right? R1 plus R2 will give you the total resistance of that circuit connected in series. But if that was the case for parallel circuits, it will be the reciprocal of the summation of series that will be equal to the reciprocal of total resistance. In that case, if I have to write this down, this is how the equation would look like. 1 over the total resistance is equal to 1 over R1 plus 1 over R2. And from this, you just have to do LCM on the right hand side and then cross multiply to find out the total value for resistance in this parallel combination. Okay. Now in question 1, it says that which combination of resistors has the smallest total resistance? We have to find out the total resistance for all the combinations first in order to identify the correct answer. So for that, for example, over here, this is connected in series, right? Series means we're just going to add the two values together, which is 2 plus 2, that's 4 ohm. This is again in series, which is RT, which is 1 plus 1, that is 2 ohms. And for B, this is connected in parallel, because you have to understand why this is connected in parallel, because now they have a junction, right? These dots are known as junctions where current gets divided, but voltage remains same. Now over here, the formula would be what? 1 over RT, 1 over 2 plus 1 over 2, which is basically 1 over total resistance is equals to 1 over 2 plus 1 over 2 is 1 by 4. If you just cross multiply it, right, then you get that total resistance as 4. Okay. And sorry, wait, one minute. Half plus you get 1, right? Sorry. Yeah, sorry, 1 minute. So you get 1 over here, and even if you do cross multiply, the answer would still remain 1. And for this one, you are going to get 1 by 2 plus 1 by 2 is 1. And for this combination, we are going to get 1 by RT is equals to 1 by 1, right? Over here, the individual resistors are also 1. So 1 by 1 plus 1 by 1, which is just going to be 1 plus 1, so just again 2 ohm. So they were asking to find out the smallest resistor, right? The smallest resistance among all the current, among all the circuits. Now, obviously option C, so option B is the one, because for option A, you get 4 ohms. This is 2 ohms, this is 2 ohms. C and D are equal. A is 4, whereas B is 1. So obviously option B over here represents the smallest current, smallest voltage. Sorry, smallest resistor. So option B is the correct answer. Okay. After this, we're going to move on to the next question. I hope this question was clear enough for all of you to understand. And these things are quite very important to memorize. How the series circuit, what changes, what divides. In parallel circuit, what changes, what divides. And obviously the resistor formula for series and parallel, right? This is extremely important. Now, I would say this question was extremely tricky because it's extremely tricky because we have to take the graph readings and everything. Okay. Now, always remember one thing is that in cases for series, right, how much one component is going to receive amount of voltage depends on the resistor also. For example, if a resistor whose voltage is, so if a resistor whose resistance is 8 ohm and another resistor of 2 ohm is connected in series, in that case 8 ohm resistor will receive a higher current, a higher voltage than that 2 ohm resistor. So higher the resistance, higher the voltage intake. So we're going to write it down over here. In series, this is only possible in series connection. high voltage intake. It's not going to be the same always. For example, if I'm going to use two resistors of same resistance, then surely the total voltage will be equally divided among the two resistors. But problem arises when the two resistors doesn't have equal resistance. For example, the first resistor have 8 ohms, the second resistor have 2 ohms. In that case, whatever the ratio that is present in between the two resistor, according to that ratio, the total voltage will be divided. Okay, we'll come across the same kind of maths a lot. So let's just start over here. Now it says that the graph shows relationship between the potential difference and current for a fixed 20 ohm resistor and a filament lamp. Always remember that a filament lamp, like for a filament lamp, its resistance changes, right? Initially resistance is extremely low. As time goes on, because of its temperature increase, the resistance will also increase. So our resistance of filament lamp changes. Okay. Now it never say that resistance of the filament lamp was negligible. I mean, we know by default that resistance of filament lamp always changes due to the change in temperature. Okay, now it says that the resistance and lamp are placed in series to the 9-volt battery of negligible internal resistance. The battery itself doesn't have any internal resistance and the battery reading was 9 volt. Now, what would be the current in the circuit? In order to find out the current, we have to also find out the resistance of this filament bulb, right? But how can you find out the resistance of the filament bulb? You have to always remember that at the end of the day, whatever voltage, obviously in this situation, as the fixed resistor and the bulb are connected in series, right over here, when they have stated that they are connected in series, this only indicates that obviously voltage is divided in between them. Voltage is divided. But we do not know in what ratio because we do not have the resistance value for that filament bulb, right? That is missing. But I would know that whatever the ratio is, their final total voltage is supposed to be 9, right? 9 voltage. Like whatever this is X and Y should always sum up to 9, right? Because obviously 9 volt is the total package, right? That can be divided among the two resistors depending on the resistance that particular material has, particular component has. But problem is we know the resistor for this fixed resistor 20 ohms, but we do not know the resistor for this bulb over here. That's where the graph plays a role. On the graph paper you have to choose a point where the total current is same for both the resistor and the filament bulb, and the y-axis coordinates are going to add up to 9. Okay, so in this situation you're going to find out one point where the y-axis coordinate is going to add up as 9, and they will also represent the same amount of current, because in series what happens, current stays same, voltage changes, right? So they will have different voltages where the obviously different voltages are going to add up and give you the result as 9, but for the two different voltages current will be same. So now over here if you focus on the graph, 9 can be broken down into what values? 9 can be broken down into 4 and 5, right? So if I'm going to write 4 and 5, this is approximately 5 and this is approximately 4. For 4 and 5, wait 1 minute. Right, we do not actually have any value. For example, obviously 4 and 5 gives you 9, but problem is at 5, yes, you get a y-intercept over here, but at 4 the y-intercept is not same, right? At 4 the y-intercept is greater than 3 point something, which is not correct because sorry, the x-intercept so has to be same because current is same, right? So you have to choose one combination of voltages where the current will be same for both the components. Now over here you get one current of that a resistor as almost 0.28 and that bulb as almost 0.35, right? Which is obviously not correct. That means we cannot choose 4 and 5. But if you choose 6 and 3, right? This is where 6 is, and 2 point, this is where 3 would be, right? For exactly at 3, you also get the same amount of current. Now if you see on the x-axis the current is 0.3 and obviously 6 and 3 add up to 9 also. So in that case the total current in this circuit was 0.3. So you get 0.3 over here. So this is how you're going to take readings from the graph to find out the total value. I hope it was clear enough for all of you to understand. We're going to move on to the next question. two identical resistors are connected in series have a total resistance of 5. Like whatever the individual resistance are, their combinations is 8. So not 5, 8. That means R1 plus R2 is 8, right? And they want you to find out what would be the total resistance when those same two resistors are connected in parallel. Now problem is that I have already, like they have already stated that the resistors are identical, right? So if the resistors are identical, then R1 and R2, they are going to sum up as X. They have the same resistors. That's why they are known as identical over here. So which means that X plus X is going to be 8, which is obviously X is equals to 8 over 2, which means 4. That means the individual resistors were 4, like the individual resistors have a resistance of 4 amps, and we need to find out the total resistance of these resistors when they are connected in series, so when they are connected in parallel. So this was the working for series part. And for parallel combination, that's going to be 1 over R1 plus 1 over R2, that is equals to be 1 over RT, which is 1 by 4 plus 1 by 4, which is 1 over RT. And on the left hand side, now you get 1 over 2, 1 over RT. If you just cross multiply it, you're going to get RT is equals to 2, which means the total resistance, like these two resistors, identical resistors, when they're going to be connected in parallel combination, the total resistance will be equal to 2 ohms. So option B will be the correct answer over here. I hope this entire working is clear for all of you. Okay, we're going to move on to question 4. It says that the graph shows how the current varies with potential difference for an electrical component. Okay, how the current varies for potential difference for an electrical component. We can clearly see that initially it is less steeper, finally it is more steeper, which means that initially resistance is very high and finally resistance is extremely low. This is actually the graph for negative temperature coefficient conductors, right? So let me just write this down. Negative temperature coefficient conductors. Sometimes I understand that I'm explaining a few more things extra which are not even required for the question, but these are required for the general knowledge, which will be obviously used in some other parts or in some other questions, right? So there's no harm to understand which graph is this from or is this of. Okay, now it says that which row of the table gives the resistance of the component at V2 and describes how the resistance changes from V1 to V2. Okay, now obviously as this is for a negative temperature coefficient conductors, which means that we can also clearly understand from the graph's shape that initially the graph is less steeper, like at this highlighted portion, graph is less steeper. Less steep, which means gradient is small initially, which means sorry, wait, yeah, less steeper, which means gradient is smaller, so small gradient. Wait 1 minute, this is for I against V, right? Over here the gradient will not give you resistance because for gradient it's supposed to be V over I. So this is for negative temperature coefficient conductors. 1 minute. Wait, let's just do this thing extra over here because as we're trying to identify the component, right? If I'm going to draw this same graph but reverse the directions, which is basically I'm going to put V on the y-axis and I on the x-axis, the graph will be like this, right? In that case, initially the graph is less steeper, initially the graph becomes more steeper then, and finally the graph becomes less steeper, which means that initial section, it is more steeper. More steeper means now a higher gradient, which will give you higher voltage, right? So a higher resistance. So high gradient gives you high resistance. Okay. And for the final section, for example, in this final section, 1 minute. In this final section now, over here you have less steeper. For that less steeper graph, it has like what, smaller gradient or smaller resistance, right? So small gradient, small resistor. So which we can clearly resistance, which we can clearly understand at this point that obviously over time resistance decreases, right? Another thing, and with in this question, if you focus specifically, they are trying to find out the resistance of the component exactly at point V2. They have not stated that we want to find out the resistance of the component up to point V2. In that case, we could have used the coordinates of V1 also, but they're only trying to find out the resistance at point V2, which means that for this specific point, we're only going to use this specific voltage and this specific current I2. So for resistance, it's just going to be V2 over I2, and for the resistance of the entire circuit along this entire graph decreases over time, right? Initially was a higher resistance, finally was at a lower resistance, so decreases over time. In that case, option D is the correct answer. I hope this was clear to all of you. This was only the explanation which I think was correct. Other than that, there was nothing much important for this. Okay, so we're going to move on to the next question. Again, we can see that there are four resistors connected in parallel. If I'm going to name, these two are connected in series, and again these two are connected in series, and overall these four are connected in parallel because you have these junctions over here, right? Always remember, at junctions current gets divided. Okay, at junctions current gets divided. We need to find out the total uh, resistance between the point X and Y. So before we find out that, we are going to combine these two as one and these two as one. I mean, if these first two resistors at the top branch are connected in series, the calculation is very easy, right? For R1 plus R2, which is just going to be 8 ohms. And again over here is going to be 8 ohms. And these 8 ohms resistors are connected in parallel to across the two branches. And now we're going to do the same working. 1 over 8 plus 1 over 8 is equals to 1 over RT. 1 over 8 plus 1 over 8 is 8 plus 8 is 16 over 64. Wait 1 minute. And this is 1 by 4 then. 1 by 4, 1 by RT, we just do cross multiplication and you get RT as 4 ohms, right? In that case, option C is the correct answer. Okay, then C is your correct answer over here. Okay. After this, again, similar calculations. At first, I'm going to, like solve these parallel combination, which is 1 by 4 plus 1 by 4. I'm going to write resistance of one, like total parallel combination resistance, which is 1 by 4 plus 1 by 4. This is going to be 1 by total parallel resistance combination is 1 by 2. So in that case, total parallel resistance combination is going to be 2. Okay, now the parallel combination resistance is 2. Using this 2 and another resistor of 4 amp was connected in series with this parallel combination. Now we can write just for the series combination now. Okay, right. This is for the parallel combination, by the way. Let me write this at the top. Parallel combination, and again for the series combination now, which is this 4. The formula is easy, right? Now we have this what, 2 resistors, because now this total combination is only giving you 2 ohms. So now we're going to write one resistor was 4, the other entire combination was 2, which is RT, is equals to 6 ohms, right? So obviously option B is the correct answer over here. This was it. Moving on to the next. When a semiconductor has its temperature increased, obviously semiconductor means they're talking about thermistor over here, right? Has its temperature increased from room temperature, that means higher than 25 degrees Celsius, its resistance usually decreases. That's because this is actually also a 4 mark question. Sometimes in electricity, they're going to ask this in MCQs, they're going to ask this in 4 mark questions. So they're quite related. If you understand the concept clearly for once, you can obviously solve the MCQ and that star mark questions easily. This is obviously talking about negative temperature coefficient conductors, right? So for negative temperature coefficient conductors, what happens initially at room temperature, but at a lower temperature, right? Their number of charge carriers per unit volume is very low, but as temperature increases, right, as temperature increases, their resistance decreases because their number of charge carriers per unit volume increases. So if the number of charge carriers per unit volume increases, this is how I'm going to connect this entire concept. When temperature increases, okay, when temperature increases, these lead to number of charge carriers per unit volume, which is basically NE, right? Number of charge carriers per unit volume. This also increases, sorry. This also increases. And then again, according to your equation, I is equals to N E. The formula is actually I is equals to N A V E, but I'm just going to write N E together, right? N E A V. Now, in this situation, is number of charge carriers per unit volume increases, current would also increase because they are obviously from the equation it is clear that they are directly proportional, right? If they're directly proportional, if one quantity increases, the other would also increase. And because of the increase in um, charge carrier per unit volume, because of the increase of the number of charge carriers per unit volume, the current would also increase. And then again, according to your second equation, V is equals to IR. Current and resistance are inversely proportional, right? These are inversely proportional. So if current increases, resistance is supposed to decrease, right? So in most of the cases for thermistors, what happens when temperature increases, the number of charge carriers per unit density is the most responsible one who actually causes the decrease in resistance, right? This is like a labyrinth over here. The number of charge carriers per unit volume increases, which increases the current, and again for current and resistance are inversely proportional. As current increases, resistance would decrease. Okay, so in that case, we can clearly understand D is the correct answer, right? And if we are talking about positive, like if this question was asking about positive temperature coefficient conductors, then the answer would be the electrons are moving faster, right? The drift velocity would increase for that positive temperature coefficient conductors. Like why for the filament lamp, right? Why for the filament lamp increase in temperature causes increase in resistance? That would be because in filament lamp, increase in temperature increases the drift velocity. If drift velocity increases, wait, am I being wrong? Sorry. If no, wait, sorry. Then it was not it was not right. The electrons are moving faster. No, the number of atoms. Yeah, sorry. For your filament bulb, this was supposed to be a little different, slower. Right, the drift velocity decreases because now there are more electrons passing through the wire. So your electrons moving, your drift velocity decreases. So if at a for a positive temperature coefficient conductors, when temperature increases, their drift velocity decreases, so current decreases. For the decrease in current, their now obviously resistance will increase, right? Again, to the same equation, V is equals to IR, since current and resistance are inversely proportional. Okay, now this would be the correct answer for filament bulb. But as we are not talking about filament bulb, so nothing to get concerned about it. Okay, the resistance of a negative temperature coefficient thermistor becomes zero at a certain temperature. No, wrong. Decreases as the temperature decreases. No, for thermistors, if the temperature increases, right? In that case, resistance decreases. Negative temperature coefficient conductors indicates that the resistance and temperature are inversely proportional. Negative temperature coefficient conductors indicates that resistance and temperature are inversely proportional, but positive temperature coefficient conductors indicates that temperature and resistance are directly proportional. Let me just write this down over here very quickly. Um, Positive temperature coefficient, temperature and resistance are directly proportional. Temperature is inversely proportional to resistance. Okay. In that case, increases as temperature decreases, right? Option C is the correct answer. Other than that, all the answers are wrong. This would be the correct answer for positive temperature coefficient conductor, which is filament bulb, right? Conductors. Yeah, other than that, B and C, sorry, A and C doesn't have any, A and D doesn't have any valid relations over here. Then, yeah, after this, we are done with the resistance MCQ. Now we are going to start with potential difference MCQs. Okay. So for potential difference MCQs, it says the first question over here. Okay, sorry, as I was saying, the diagram shows a potential divider circuit that contains a negative temperature coefficient conductor, okay. Now it says that the temperature of the room containing the circuit increases, which means the temperature increases as we're talking about negative temperature coefficient conductors, right? For negative temperature coefficient conductors, if temperature increases, resistance would decrease. They are inversely proportional. So let me just write this down over here very quickly. Negative temperature coefficient conductor, temperature inversely proportional to resistance. So in that case, temperature of the room increases, which indicates resistance of that thermistor X, right? Let me just write it down like this. Rx decreases. And Y was fixed resistor. So for Y, there will be no change, but X will have a decreased resistor. And again they were connected in series. It says that select the row of the table that correctly shows the changes in readings of the meters. Now over here, if we have to think it like this, that obviously if the resistor of the thermistor is decreasing, that means the total resistance is also decreasing, right? Because if in thermistor previously, if it had a voltage, if it had a resistance of 4 ohm and Y had a resistor of 3 ohm, right? Then the total resistance was 7. But now at a higher temperature, the resistance of that X would decrease. Maybe it now decreased to 2 ohm, right? The resistance of Y is still 4, but the resistance of X is now 2. Or the resistance of Y is still 3, but now the resistance of X is 2. So 3 plus 2 gives you 5. Previously, the total resistance for this entire circuit was 7. Now it is only 5. So obviously what? The total resistance over here decreases for the entire circuit. Only if the resistor for the thermistor decreases, that will cause the total resistance for the entire circuit to decrease. So if the total resistance for the circuit decreases, the total current will also increase. Let me write it down over here in a bar chart that the temperature increases. This causes the Rx resistance for that X to decrease. This indicates the total resistance of the circuit to decrease, as again current and resistance are inversely proportional. So a smaller resistance will create a larger current. So now you have the total current for the circuit increased, right? And another thing, since I have already stated at the very start that in series circuit, obviously voltage gets divided among the components, but voltage gets divided depending on the resistance of the component. The higher the resistance for the component, the higher the voltage that component will now have. So Since Rx is decreasing, right? Resistance for the component X is decreasing. That means voltage occupied by X component would also decrease. That means more voltage will now be available for component Y. So that means Vy will increase, Vx will decrease, and the total current among this entire circuit will increase, right? So over here, if I zoom in, Vx will decrease, right? Because the resistance of the thermistor is decreasing. V and R are directly proportional. For a smaller resistance, it is going to receive a smaller voltage. So Vx is decreasing. So either these two will be the correct answer. Vy will increase because obviously if the total voltage was like V units, right, it would be divided for the two components depending on the ratio of their resistance. So now if Vx is decreasing, obviously providing more voltage available for the component Y. So in that case, Vy will increase. Okay, and current will also increase because in decrease in resistance of that thermistor causes the total resistance of the circuit to decrease. So if total resistance of the circuit decreases, total current also will increase. So the thermistor decreases, fixed resistor increases, and the total current in the circuit will also increase. So for option B, this is the correct answer. Okay, so I should just zoom out and you guys should have one look for this one question. Okay, I hope this one was clear enough for all of you to understand. If you still have any questions, try to comment. I will try to reply as soon as I can. Question 2. A negative, again, this is about negative temperature coefficient conductors. That means thermistors, right? Where temperature and resistance are inversely proportional, are connected in the circuit as shown. Okay, a cell has a negligible internal resistance. That means small r is not over here. Internal resistance is 0. And the effect of decreasing the temperature of the thermistor is that obviously total resistance will decrease, total current will increase, right? These are the only effects. Also the voltage, yeah, that is it. The ammeter reading will decrease. No, the ammeter reading will increase, right? So the ammeter reading will increase. Now the voltmeter doesn't actually have any change over here because there was no other component added with this thermistor in series, right? If it was, then we could have seen some changes in the reading for the voltmeter. The voltmeter, in this case, the voltage is not divided because there was no other component in this circuit. Only this thermistor was present. So there will be no division of the voltmeter. So voltmeter reading will not change. Even if the temperature is same, even if the temperature increases, the voltmeter reading will remain same. Voltmeter reading won't change. The only thing that would change over here is the current. As at a smaller, oh wait, sorry, at a smaller temperature, there will be higher resistance, so current will decrease, right? Decrease in temperature causes higher resistance, so current decreases. So in that case, option A is the correct answer over here. Yeah. Other than the same explanation was correct, the total voltmeter reading will not change. Then over here we have similar kind of maths. The battery in the circuit has negligible internal resistance and the total EMF is 12. The potential difference across the parallel combination is, okay, to identify the potential difference across the parallel combination, we have to find out the total resistance for this parallel combination. So I will, draw a simplified diagram. For example, I will think of it as one resistor, and I'll consider the parallel combination as one resistor as a whole, and these two resistors are connected in series. This is your parallel combination, and this is your R1, which was given as 200 kilo ohms, right? So I'll first try to calculate the value for your parallel combination resistor, which is obviously 1 by Rp is equals to 1 by 100, so 200 and 1 by 200, right? I'm going to name these resistors over here. It's just very easier for me to explain them. 1 over Rp parallel combination. Wait 1 minute. Rp, that is going to be 1 over R2 plus 1 over R3 because resistor 2 and resistor 3 were connected in parallel combination. So 1 over Rp is equals to 1 over 200 plus 1 over 200, which is going to be 1 over 100 at the end, right? So in that case, RP is eventually going to be 100 kilo ohms. Like this entire parallel combination now have a total resistance of 100 kilo ohms. So this is 100 kilo ohms. The kilo over here doesn't actually play an important role. Remember the total voltage over here was 12 volt, right? So now because of this 12 volt, obviously it will be divided like equally, like divided in between the two resistors depending on their resistance. Now this is how the entire equation arrives. This is how the entire calculation will be. For example, if for that part, we would still need to find out the total resistance for this entire circuit. So for RT, now this is equal because now it is connected in series. It's just basically the summation of the individual resistors that will give you the total resistance. So it will be R1 plus RT, that is 100 plus 200, which is 300 kilo ohms. Now this is how you're going to create the equation. Now always remember that these ratio, no, this ratio, yeah, okay, sorry, yeah, no problem with that. Okay, as I was saying, you want to find out the voltage for that parallel combination, right? So VP divided by RP is equals to V total divided by R total. Exactly why they are equal, if you think of it, that's because voltage over resistance gives you current, right? If these are connected in series, obviously what? They have the same current flowing through each one of them. So voltage over current, whatever the current that is passing through this parallel combination will be the same current that will be passing through the battery also. That's why these ratios are equal. So, I mean, that was just an extra knowledge I provided. Not that much related for this calculation. If I'm going to only focus on the calculation for VP, voltage across that parallel combination, VT was 12, total resistance was 300, and RT was 100, right? So you just get 4 volt. That means out of those entire 12 volt from the power supply, your parallel combination will only receive 4 volt, whereas it's clear now the R1 would receive 8 volt, right? Because 12 minus 4 is 8. So option B is the correct answer over here. You guys can have a look over here and let me know if you have any problems. We'll then move on to the next question. Okay. This question was also a little tricky, I would say. How many questions are left? 5. Okay, so as I was saying, now over here it says that in the circuit shown, the battery has negligible internal resistance. L, M, and N are identical lamps. Identical lamp means that they have the equal resistance, right? Identical means this always indicates that they have equal resistance. So now it says that the filament lamp M breaks. This one is going to break, okay, which means that identify the row of the table which shows the resulting changes in the brightness of lamp N and N. So N and L. Okay, now what happens over here? L and M were connected in parallel, right? Just for a better explanation, I'm going to assign each resistor with a numerical value so that you guys get a better understanding of the concept over here. So I'm going to consider Rn as 2 ohm, RL as 2 ohm, and RM is as also 2 ohm. Obviously, they were stated at the very start that these are identical resistors, right? Identical resistors means that they are all going to have the same amount of resistance. As I was saying, so I'm just going to use this number for a better explanation of this equation. Now they are saying that RM stops working, right? So if RM stops working, what exactly happens? Focus on this. Like if RM was working, then how was the calculation and what happens when RM stops working? I think I have space over here, right? Okay. So I'm going to write it down as if lamp M was working then, right? When lamp M was working, the total connection, like this entire thing is a parallel combination then, right? L and M are in parallel. So we have to write L and M gives you RP, parallel combination resistors. So in order to find out RP, that would be 1 over 2 plus 1 over 2, which will give you 1 over rp as 1 over 1, right? Half is 1 basically. So you get the rp as 1. Now, if you want to find out this Rp and that Rn, right, the component n was connected in series, right? This component, this entire combination, and this component n are connected in series. So, in that case, we have to again write this down. Let's just highlight these. Rp, like the parallel combination, and the component n are connected in series. Now you can find out the total resistance of the entire circuit, and that would be what? RT is going to be Rp plus Rn, which is 1 plus 2, that would be 3 ohms, right? Now over here, what happens is that if you focus on this diagram, right, if the total voltage, I'm going to assign the power supply with a voltage also, that is, I'm considering this as a 6 volt, okay? In that case, out of the 6 volt, right, this 6 volt will be divided into 2 is to 1 ratio. 2 is to 1 ratio means that because it has 2 voltage and this entire combination has 1 voltage. In that case, this voltage, this resistor was going to get 4 volt out of that entire voltage, and this entire parallel combination was supposed to get 2 volt, right? How can I understand that? I can obviously calculate that also. I'm just going to squeeze it over here, and I'll do the calculation in this part, that what was the voltage, right? Voltage received by lamp L, or what was the voltage received by the entire parallel combination or by that lamp N. Rp divided by the formula should be Vp, right? Because current remains same. Vp over Rp is equals to V total over R total. Our VP was unknown, right? V total was, I assume it as 6, RT was 3, I calculated it, and RP was 1. So you get 2 volt, right? So out of 6 voltage, right? Only 2 volt will be received by the entire parallel combination, and Rn will receive 4 volt itself, right, for itself. So now, which from this calculation I can understand that, like, how much each for each component was supposed to receive at this condition. um, Vn, sorry, Vl and Vm, as they were connected in parallel, they're going to receive the same amount of voltage, right? So Vl and Vm would get 2 volt, whereas Vn now will get total minus, total was 6, sorry, 6 minus 2, that voltage will be 4. Now, obviously, we can clearly understand that previously the voltage occupied by component N was extremely large compared to the combination of L and N, right? Now, these were all the workings for your under the theory when M was still working. But now we are going to assume that if M stops working, right? This is for when M not working. So when M is not working, the entire circuit will be different, right? If M is not working, then the circuit only has this L and N present, where they are going to be connected in series only. If I'm going to draw a very small diagram, this is how the diagram will look. This is L, this is N, and this is L. M doesn't have any existence this time, because if M is not working, current is not flowing through them. So M is entirely turned off for me, right? M is not valuable for me at this point. I'm only going to focus on L and N. Obviously, N has a resistance of 2 ohm. This is 2 ohm. Now I can clearly understand the total resistance can be easily calculated by RL plus RN, which is going to be 2 plus 2, which is 4 ohms. Right, in this situation, now you have to clearly understand that this time the resistance of the two components are now equal. When M is not working, L and N now have the same resistance, equal resistance. If they have this equal resistance, that means previously I assumed the total voltage was 6 volt, right? Now they're going to receive equal amount of voltage because they have the same resistance. So now I can say voltage of L is and voltage of N, they are both now 3 volt each. If you compare it with the previous case, previously voltage of component L was 2, now voltage of component L is 3. So for the component L, voltage increases, But previously voltage of N was 4, voltage of N now is 3. So from 4 to 3, there is a drop in voltage for N. And always remember that voltage is related to brightness, right? So for if L, voltage increases, brightness will increase. For if N, voltage decreases, brightness will decrease, right? So we can write for voltage L increases, increases, so brightness increase, right? Brightness, brightness increase. And for voltage N, um, this voltage decreases, and if decreases, it would indicate brightness decreases. So this is it. That means from this entire mathematical calculation, it was easier for me to explain this question to all of you, which means that L increases, N decreases, which is option D is the correct answer. I could not think of any other possible ways for this explanation. I thought explaining with numbers was easier than with explaining with words and alphabets. So if anyone have any other ideas to explain this question much more easily, please write an email to me explaining this question. I would appreciate it. Okay, now this was the entire working for question 4. I hope question 4 was clear enough for all of you to understand. Certainly not easy, but we can work our ways around it, right? Okay. Obviously not a specific question for 1 mark, right? This is like a very long question and not worth just 1 mark. Okay, we're going to move on to question 5 over here. For question 5, it says that the diagram shows a uniform wire XY across a potential difference V naught is applied. Which of the following correctly shows the output potential across XZ? Always remember that longer the length, higher the resistance, because for a longer length, currents would have to travel a longer distance, right? When they're going to travel a longer distance, they will produce more heat energy, right? And for a longer wire, higher temperature obviously indicate higher resistance. So in that case, longer length, which means for XY, they will have a higher resistance, and for XZ, that will have a smaller resistance, right? Now, how can you find out that? They want you to find out which of the following correctly gives you the total output potential for XZ only. Okay, another thing to remember over here, XY gives you the total resistance for the circuit because that is the total length, right? And XZ is like a partial resistance of the circuit. Now, if you want to find out the equation, you have to use that same series combination also. Like XY is a resistor with higher voltage, or the total voltage. XY is actually your, sorry, XY is actually your total resistance in this case, and XZ is like a partial resistance, like R1 or something. So in that case, R, obviously they're connected in series, so they will have the same current, right? So V1 over R1 is equals to V total over R total. V1, we're trying to find out that V total was V naught, R total was XZ, XY, and R1 was XZ. I'm just going to rearrange it. So I'm going to write XZ at the top, XY at the bottom, and then V naught in the side, which means this is exactly XZ, XY, V naught. Option B, right? Option B is the correct answer then. Okay, then this is it for potential difference calculations of MCQs. Now we're going to move on to the internal resistance and EMF. Okay. It says that the potential difference of 6 millivolt applied across a circuit component, what is the energy transferred when a charge of 2 coulomb flows through the component? Like we have the voltage, we have the charge, we just have to find out that energy, right? E is equals to VQ, which is 600 multiplied with 10 to the power of negative 3 multiplied with 2. Okay, 6, 10 to the power of negative 3, right? So 1, 2, 3. Yeah, that's going to be 0.6. So 0.6 multiplied to 2 is 1.2. If you do the calculation, you're going to get 1.2 joules. So option D is the correct answer over here. Okay, and then again, from this part, whenever they are asking you to find out the internal resistance, what are they trying to find out? Which of the following correctly gives you the potential difference across the internal resistance? Okay, now they are trying to find out the potential difference across the internal resistance. Always remember, in series circuit, right, over here this capital R and small r are connected in series. That means a V1, like the total voltage over here, is going to be the voltage of the separate components. Like voltage of this fixed resistor plus voltage of this internal resistance is going to be equal to your total EMF, right? And we can break this down easily. For example, hmm, 1 minute. They have these values, but this was all written in terms of R, right? Okay. They have not included any I in this case. There was a derivation for it. For example, I'm going to derive, like I'm going to break down the equation for this VR, which is I multiplied with current, right? And oh wait, they're not doing this actually. Sorry. Over here, what they're doing is that for this case, they have this VR divided by the smaller internal resistance is equals to EMF over the total resistance. This is connected in series. That means what? R1 plus R2 will give you the total resistance, right? So R1, like capital R plus small r. In that case, if you just make V smaller the equation subject of this equation, EMF capital R plus small r multiplied with that small r. So you can just rearrange it and write it as small r EMF capital R plus small r. That will give you the voltage across that internal resistance, which is exactly in the form of option B. So option B is the correct answer. So not option B, option D, right? Option D has that internal resistance at the top, right? This one, right? So option D is the correct answer over here. Over here, they're still using the same concept. Current is same, so using that ratio between the voltage and current to find out the voltage of this internal resistance. 12 volt connected to this circuit, potential difference across the point A and B. Okay, so in that case, obviously, we're going to consider these as RP, right? Parallel combination. For that parallel combination, it's going to be 1 over RP, 1 over 6 plus 1 over 6, which is 1 over RP. 1 over 6 plus 1 over 6 is going to be 12 over 36, right? So 1 over 6 plus 1 over 6. That's 1 by 3, right? So if it is 1 by 3, in that case, a parallel combination now have a total resistance of 3 and the total voltage was 12, right? So in that case, total resistance will be 6 plus 3, that would be 9 volt. And then again, if you want to find out the voltage across that VAB only, voltage across the AB, VAB divided the total resistance across the point AB was 6 and total voltage is 12, total resistance is 9. So you get VAB as 12 over 9 multiplied with 6, so which is 12 over 9 multiplied with 6. Wait, maybe I made a mistake. 2 by 3, 4 into 2 is 8, right? So why am I getting this? Oh wait, I'm actually using my phone, so it's 72 by 9, this is 8, right? So the answer is 8 volt. Option C is the correct answer then. And moving on to the last question actually. Over here it says, which of the following is the correct expression for the current I in this case? For current I, the equation is always, again, it starts with this, that total EMF is equals to voltage of the fixed resistor plus voltage of the internal resistance, right? No, we can just find it out like this, that total resistance over here is just going to be R plus internal resistance, because internal resistance and fixed resistor were connected in series, right? So in that case, For current, it's going to be total voltage divided by total resistance. For total voltage, it was EMF, and total resistance, it was R plus small r. So EMF, R plus small r, option C is the correct answer in this case. Yeah. This is it for all the MCQs of Electricity Unit 2 is Physics. I hope it was clear enough and it made your concepts about Electricity Unit 2 a little bit more clear. If there is any questions, any request, you can obviously email me in my email address, moimahamed01@gmail.com, and also you can WhatsApp me, you can inbox our Facebook page at ExcelEasy. So yeah, this is it. Thank you for joining.